Hello friends, welcome to the lecture series on engineering graphics. I am Dr. Shivraj Narayan, Professor of Mechanical Engineering at VNR VJEC. In today's session, we are going to learn about engineering curves and especially the conical curves. The learning objective of this session, you are going to learn about the concept and formation of conic sections using a cone and cutting plane. Also, you'll be learning about the general method of construction of conics in engineering graphics for the construction of ellipse, parabola and hyperbola. So why do we have to learn about these conical curves? So in our day-to-day life, we find plenty of applications wherein these curves are used. For example, if we take the case of orbit of the planets, all our planets, they are orbiting in an elliptical path. So whatever this image is being shown, it is for the elliptical curve. Similarly, we have the dish antennas. They also represent the engineering curve. Then we have the bridge structures. As you can see over here, the Chenab railway bridge. So this also represents an engineering curve. Then we have got the fountain jets. So they represent the parabolic curve. Similarly, we have the hyperboloidal gear as well as the cooling towers that are used in the nuclear thermal power plants. So these applications, they indicate that engineering curves are very much needed in our day-to-day life. So how are we going to draw them? How are you going to construct them? Now before doing that, we should know about the basic concept, how we have arrived at these curves. So in order to understand this, we'll try to first know what is this. This is a right circular cone. So we'll try to understand this terminology. So we have the topmost is the apex, and then we have the base. This apex and base, they are connected using slant lines, which we call them as generators. So there are many generators. For representation, we have shown only two, one on the right side and another one on the left side. A line which joins the apex with the center of the base is called as an axis. So this is an imaginary line. The line that starts from the apex and goes up to the center of base is the axis. Now what we do is, we take this right circular cone and we cut it using a cutting plane. So this cutting is done with reference to the position of the cutting plane with reference to the axis. So if we take the cutting plane as parallel to the base and perpendicular to the axis and cut it, that means if you take sort of a horizontal position of the knife or the cutting plane and cut this cone, then what shape we get is a circle. And that is what is represented over here. You can see the green color is the cutting plane, and then we are cutting this cone such that the cutting plane is perfectly horizontal. That means it is parallel to the base and perpendicular to the axis. So this is what is the first curve. The next one is the ellipse curve. Now how do we get this ellipse curve? So for obtaining the ellipse curve, what we do is, we make use of this cutting plane such that it is inclined to the axis. The cutting plane is inclined to the axis and is on one side of the apex. So that is where we are getting the elliptical curve. The next one is the parabola curve. So how do we get the parabola curve? The parabola curve is obtained by cutting the cone such that the cutting plane is parallel to one of the generators. So you can just see here, it is parallel to the generator. And the last one is a hyperbola. So hyperbola is basically a pair of curves, and for that purpose we need two cones which are directing towards each other. So what we do is, we take a cutting plane and we position it such that it is parallel to the axis of the cone. So when we do the cutting, whatever is the leftover solid, on that solid the shape that is formed is basically hyperbola curve. So in simple terms, what are engineering conics? These are nothing but the sections obtained by cutting a right circular cone using a cutting plane at different positions with reference to the axis. So this is what is the theoretical information about conical sections. Now how do we construct them graphically or geometrically in engineering graphics? So for doing that, we have a method called as general method of construction. It is also known by other name, focus directrix method or the eccentricity method. So these are the common names that are generally used for the construction of engineering conics. Now before we dwell into this general method of construction, we'll try to understand the terminology that we should know which will be used in this method of construction. So here you are able to see a straight vertical line AB. This line is called as fixed straight line and its name is directrix. AB is the vertical line whose name is directrix. Then exactly perpendicular to this line we have a line called as CC. This is the axis. So AB is the fixed straight line which is vertical, and a line perpendicular to it is the axis line. Then we have these three curves: ellipse, parabola and hyperbola. These three curves, as you can see, they are different. Why? Because ellipse is a closed curve, whereas parabola and hyperbola are open curves. Now what is happening? These curves, they are cutting the axis at certain points. For example, you can see ellipse is being cut, ellipse curve is cutting the axis at this point, so it is V. Similarly, parabola is also cutting the axis at this point, we are designating it as V. So what is this V? V is nothing but the vertex. Vertex is a point at which the curve cuts the axis. So since ellipse is a closed curve, we get two vertices. So for ellipse, everything will be 2 in number. It will have 2 vertices. Similarly, we have one focus, a fixed point. So for ellipse, we will have 2 focus points. So we call it as foci. So F and F dash are the foci, V and V dash are the vertices of ellipse curve. Whereas for the parabola and hyperbola, we will have a single vertex and a single focus. So next, what we are doing is, we are showing one point P on the curve. So you can see on ellipse we have shown a point P. Similarly, we have shown a point P on the parabola, and we are also showing a point P on the hyperbola. So now what I can do is, I can measure the distance of this point P from fixed point F, that is from focus. So I can measure this distance PF. Similarly, I can measure the distance of point P from the fixed straight line directrix. So which we are calling it as a point D on the directrix. So I can measure this distance P to D. So I have measured PF and I have measured PD. If I take the ratio of these two distances, then I get something called as a constant. Same way I can do it for parabola as well as hyperbola. So I can measure the distance of point P from the focus F. Similarly, I can measure the distance of point P from this directrix. If I take the ratio of these two, I get a constant. So this constant is already standardized and found out. So here it is shown as, for parabola, that constant is equal to 1. For ellipse, it is less than 1. And for hyperbola, it is greater than 1. So what is this ratio? This ratio of PF by PD is nothing but eccentricity. The ratio of PF by PD is nothing but eccentricity. Eccentricity is denoted by small e. So for ellipse it is less than 1, for parabola it is equal to 1, and for hyperbola it is greater than 1. Now, in order to further simplify this, what I will tell is, the way we have assumed that P is a point on curve, I can also say that vertex V is also a point on curve. We know that vertex is the point at which the curve cuts the axis, but it also lies on the actual curve. So the way we say that point P is a point on curve, similarly I can say vertex V is also point on curve. Now I can apply the same principle here. I can measure the distance of this vertex V from focus F. Similarly, I can measure the distance of vertex V from fixed straight line directrix. I can take the ratio of this, and that will also be constant. So this is given by eccentricity. So eccentricity E is equal to PF by PD, which is nothing but equal to VF by VC, which is equal to constant. And these constant values, as I have already told you, for ellipse it is less than 1, for parabola it is equal to 1, and for hyperbola it is greater than 1. So since we are making use of these ratios for the construction of these curves, this is called as the eccentricity method. So what is eccentricity? It is nothing but the ratio of distance of a point from the fixed point focus and its distance from the fixed straight line directrix, that is nothing but eccentricity. Now let us move towards the construction part of this. So as part of the general method of construction, we have different steps, and in order to solve that, we need certain data. So here we are taking one sample problem. So the statement says that we need to draw a straight line AB of any length. So this straight line AB of any length is nothing but the directrix. Then mark a point F 65 mm from AB. So this F indicates it is the fixed point focus. So the distance of focus from the fixed straight line AB is 65. So we also call it as the focal length. Then what is asked? Trace the path of a point P moving in such a way that the ratio of its distance from the fixed point F to its distance from AB is, we have been given three cases, 3:2, 1 and 2/3. So what does this mean is, we have been provided the eccentricity explicitly. It is mentioned that the ratio of its distance from fixed point to the directrix is given as 3/2, 1 or 2/3. So three cases are given. 3/2 means it is more than 1. So the first case is hyperbola, the second one is 1, so it is parabola, and the third one is 2/3, it is nothing but less than 1, so it is ellipse. So we have been asked to plot at least 5 points, name each of the curve, and then draw a normal and a tangent to each of the curve at a point on it 50 mm from F. So before we move on to the construction in AutoCAD, first let us understand how do we construct this. So the first case is that of hyperbola. The given eccentricity ratio is 3/2, and 3/2 is nothing but greater than 1. So we are going to construct a hyperbola. So what are the steps involved? The very first step is we need to draw the directrix line. So draw a straight vertical line AB, which we call it as directrix. Then on that line, we need to mark a point C. Through this point C, we draw a line perpendicular to the AB. So this line through C represents the axis. Next, on the axis, we need to mark the focus or the fixed point. And for that, we have been given the distance as 65 mm. Once we mark this fixed point F, we need to divide the focal length CF into number of equal divisions. So 65 mm is the focal length, and it should be divided into some number of equal parts. How many parts? So that is given by the summation of the values given in numerator and denominator of the eccentricity ratio. So since the eccentricity ratio is given as 3/2, summation of the numerator value and denominator value, that is 3 plus 2 becomes 5. So for this problem, the division will be 5 parts. So the focal length has to be divided into 5 parts. Next, after dividing the focal length into 5 parts, we know that eccentricity is given by the ratio VF by VC. What is V? V is vertex, F is focus, again V is vertex, and C is the point on directrix. So we equate this eccentricity ratio with the given value. So E is equal to VF by VC is equal to the given ratio 3/2. And now what I do is I simply compare the numerator of this. You can as well compare the denominator. It will give you the same result. So what you need to do is compare either numerator or denominator with the given value. So here numerator is VF and the given numerator value is 3. So how do I read this? I read it as vertex V is at 3 division distance from focus. And if you want to compare it with denominator, then it becomes VC is equal to 2. So it means that vertex V is at 2 divisions distance from C. So I will go with the numerator. So vertex V is at 3 division distance from focus F. So what we have done is we have already divided the CF length into 5 parts. So from vertex V, we count third division, and from the point focus F, we will measure 3 divisions and mark the vertex V. Then at vertex V, we need to draw a perpendicular. This perpendicular line length should be equal to VF. So once we draw this line V to B, what we do is we join the endpoint C on the directrix with B and extend it. Next, towards the right side of vertex V, what we do is we mark a number of points on the axis 1, 2 and 3. And through these points we draw perpendicular lines. These perpendicular lines should meet the extended line CB. So wherever these perpendicular lines meet the extended line CB, we mark them as 1 dash, 2 dash and 3 dash. After doing this, we start measuring the distance. We already have point 1 on the axis and 1 dash as the point on the extended line CB. So we measure that distance 1 to 1 dash, take focus F as center, and we draw arcs on the same perpendicular through 1 but on both sides of axis. That means we have a perpendicular line which is passing through 1. We take F as center, 1 dash as the radius, and draw arcs on line number 1 but on both sides of the axis. And the same process we need to repeat for the remaining points. So we'll measure 2 dash as the distance, take F as center, draw arcs on line number 2 but on both sides of axis. Similarly for third division and fourth division. So wherever these arcs cut those lines, they will give us points P1, P2, P3 and so on, which are nothing but the points on the conic curve. We need to join all these points using smooth curve to obtain the required conic, and in this case it is a hyperbola. So this is basically the steps that are involved in the construction of hyperbola. Similar to the construction of hyperbola, we also need to now draw tangent and normal to the curve. So this process of constructing tangent and normal is common to all the three curves, that is hyperbola, parabola and ellipse. So what we need to do is, we need to mark a point at the given distance from focus F, which is 50 mm. In this case, in this problem, the data is given as 50 mm from F. So we already have F point, we have already constructed the curve. So we take F as center, 50 mm as the radius, and we cut an arc on the curve. Next, we join that point P with the focus F using a straight line. So we now get a new line which is PF. Next, from F, we need to draw a line which is perpendicular to the PF line. So this line should meet directrix AB at S. Next, draw a line through S and P. So S is a point on the directrix, P is the point at which we want to draw the tangent and normal. So we connect S and P using a line and extend it. So this line we'll call it as ST, and which is nothing but the required tangent to the curve. Now how do we get the normal? So for normal, through this point P, we'll draw a line perpendicular to the ST line, and it should pass through the point P. So this line we call it as NM, which is nothing but normal to the curve. So these are the steps that are involved in the construction of conical curves as well as the tangent and normal. So in the next session, we will cover demonstration of the same problem in AutoCAD. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.